This conference will now be recorded.
So, very good evening, students. We are discussing JEE Advanced Papers question on the topic magnetism. So, here both magnetism and induction part will come in this section. So, we have few questions today for today's discussion. So, let us first read the question. So, this is the first question. As you see, it is from JEE Advanced paper 2015. So, so this is paragraph based question, and to solve this kind of problem we need to first read the paragraph carefully and try to understand the physics behind this paragraph, like physics given in the paragraph itself. So the question says, this paragraph says, in a thin rectangular metallic strip in a thin rectangular metallic strip, a constant current I flows along the x direction. You see here the geometry is, so along the length of this, the x-axis, okay, all right. So along the width there will be z-axis, sorry, along the width or breadth along the breadth, it will be, so this is z-axis, and along the thickness or width, this is y-axis. So this is x-axis. Okay. So the current is flowing in the x direction, as you see in the figure also. The length, width, and thickness of the strip are, length is L, then width is W, then thickness is D for this thin metallic strip. A uniform magnetic field B is applied on the strip along the y direction. See, if this is in the plane of the paper, or horizontal xy plane, so it is in the xy plane, okay, horizontal xy plane suppose, then the magnetic field applied just top to bottom, kind of that, okay. Magnetic field, uniform magnetic field B is applied on the strip along the y direction, okay. Due to this, charge carriers experience a net deflection along the z direction, okay, along the z direction. This results in accumulation of charge carriers on the PQRS. See, this is the surface, PQRS. This is one surface, and appearance of equal and opposite charges on the face opposite to that. That means this face. Okay. If I think of a rectangular slab like this, so these are the two opposite faces. So this figure is very clear actually. So you can just make out of it. So these are the two opposite faces. So where K and M, two dotted dots are there. So this is one face, PQRS. Another face is this one where K is pointed. So these are two opposite faces. So suppose in this case we'll see, so equal and opposite charges will be accumulated. Here some charges if it is positive here, then it will be negative here, or vice versa. We will see what charge is going where or which phase. So the result in accumulation of charge carriers on the PQ, RS and appearance of equal and opposite charges on the opposite phase, on the phase opposite to PQRS. A potential difference along Z, potential difference along Z. See, this is the Z axis along the width. So sorry, along the width, yes, width. Along the width, the Z axis is. So there will be a voltage develop, actually a potential develop, because if suppose there is positive charge all the way and here negative charge, so there is charge separation, and obviously there will be a potential develop between the opposite phases, and at the same time there will be electric fields also. All right, so the potential difference along the Z direction is thus developed. The charge accumulation continues until the magnetic force is balanced by the electric force. Magnetic force is balanced by the electric force. The current is assumed to be uniformly distributed on the cross section of the strip and carried by electron. See, current is uniform, it is assumed. Now we have questions. Consider two different metallic strips, 1 and 2 of the same material. Their lengths are same, with W1, W2 and thicknesses D1 and D2 are respectively different. Okay, so 2 points K and M are symmetrically located on the metallic strip. Okay, on the opposite faces of the strip. Okay, in the XY plane, V1 and V2 is the are the potential differences between K and M points for strip 1 and strip 2 respectively. Then for a given current I, the following I, then for a given current I flowing through them in a given magnetic field strength B, the correct statement. So then for a given current I flowing through them in a given magnetic field strength B, the correct statements are. So we have to find out that. So which one is or are the correct statements? Okay, similarly, we have the second part of this question. Consider two different metallic strips. So earlier it was same metallic strip of different length. So now you have two different metal strips of the same dimension, with thickness and length are same, with carrier densities are different here. Different metal means there are different carrier density, N1 and N2 respectively. Strip 1 is placed in the magnetic field B1 and strip 2 is placed in the magnetic field B2, both along positive y direction. Then V1 and V2 are the potential differences developed between K and M for strip 1 and strip 2 respectively. Assume that the current I is the same for both the strips. The correct options is or are. We have to find out which one is correct option, or there may be multiple answers correct. Okay, before I do this, let us go to the first problem itself and try to solve it. So what is the question? The question is that there are consider two different metallic strips, 1 and 2 of same material, and their lengths are same, widths are same, and thickness are also their lengths are same, but width thickness are not same, different. So 2 points K and M are symmetrically located on the opposite faces parallel to xy plane. V1 and V2 are the potential differences between K and M in strip 1 and strip 2 respectively. Then which of the following? See the current, then for a given current I through the given magnetic field strength, the correct option is. Okay, so to solve this problem, we need to first of all understand the thing is this is important. Let us just do it here. So when see this problem can be easily solved if one understands the physics in the paragraph itself. Okay, so it is given that there is a rectangular strip of certain dimension we know L, W and D. Okay, so this is the dimension, so this is the X, this is the Y and this is the Z. Okay, all right, we'll just draw the reference frame also here. Y, this is X and Z. Okay, so along the Z it is the width. Okay, so when when the current is flowing in the xy direction, sorry, x direction, and uniform magnetic field is applied along the y direction. So current, see, when current flowing along x-axis, so the v of electron is along the negative x-axis. I hope you agree with me. And the magnetic field along y-axis. So there will be, see, there will be magnetic force acts on the electrons. Q V cross B. I'm taking this is a perpendicular to each other, and only so with a minus sign here. So again, this is minus. Okay, I have taken this as minus, so I will not take this electronic charge as minus. Okay. Or sorry, I'm sorry. This can be taken as minus as well. So these two negative will give you a positive quantity. So V, VE, B. But what is the direction of the force? See, we know I, J, K. If you go with cyclic rule, see you have electrons flowing. See, if current flows this way, electron flows negative I direction, right? So let this be positive all the way. Okay, so I and I Y, so I J will give you positive K. Okay, so the electrons will be actually V cross B. Okay, so electrons are moving in the negative x direction, and magnetic field is given along the positive y direction. Okay, so electrons and positive ion cores will be there, and they will actually experience Q V cross B that I have written already. So electrons will be deflected towards the negative z direction, and positive ion cores will be deflected towards the positive z direction. Let us see how we get. So generally I cross j will give you k cap, right? Now electron is flowing in the positive x direction. That means this the velocity of electrons will be along the negative y direction, sorry, negative I direction, and this is positive anyway, so it will be minus k cap. Okay, So electrons will be actually deflected. Electrons will be deflected in the negative k direction. Okay. So q v cross b we can just use. Okay. So and for positive charges, electrons will be moving. Positive charges are generally deflected towards the positive x-axis. So here, look here, there will be all the electrons. Electrons will be deflected to the, sorry, here will be all the way positive ion cores or positive charges. So here it will be negative charges at the negative x-axis direction, and here it will be all the way positive. So when there is a surface with negative charge and another surface with positive charges, so there will be obviously an electric field like this. So electric field direction will be from electric field direction will be along negative z cap direction. Okay, because electric field will be positive to negative direction. Okay, so when there is charge separation or accumulation of charges in the opposite phases, so there will be electric field developed. So that electric field now will experience will give a force. Okay, provides a force, so that is q into e, and that must be equal to q v vb. So these two will be equal, therefore q goes off. So we'll get a relationship between electric field and electric field velocity and magnetic field as well. Okay, so due to the charge separation, a potential difference will be developed between the opposite phases, okay, parallel to the xy plane, and that will be directed from positive z to negative z direction, or we can say towards negative z direction. Okay, so I'll just clean all this. I'll just show you pictorially how electric field is here. So magnetic field is along positive y direction now. So magnetic field is along positive y direction. So the force will be QVB, that we know. Now the electric field has been developed between these two phases. Okay, so that electric field is how do you get the electric field? We get the electric field or the potential from the equilibrium situation. How equilibrium situation will happen? See, the charges will be deflected by both electric and magnetic field now, because now electric field was deflecting the charge carriers along the positive and negative directions, of z. That means these opposite phases. Now electric field will be actually suppose electrons will be actually deflected towards this way, since the electric field direction, sorry, positive charges will be deflected towards this way by the electric. So positive charges will be deflected by the electric field towards negative z direction of the face. Okay, of the rectangular strip. See, this is exactly opposite, right? So this force, see positive charges by magnetic field, like deflection of positive charges by magnetic field was there in the along the positive z direction. Now the positive, see when the electric field develop, electric field will actually give an opposite force to the magnetic force. Okay, so see the electric force here, electric force opposes the magnetic force. Okay, electric force opposes the magnetic force. And how equilibrium established? When the electric force on the charge carrier, will be exactly equal to the magnetic force on the charge carrier. So what is electric force? I am writing Q into E, and here it is QVB. Okay, so that's how we'll get an electric field, but this we have to see which direction we are getting the electric field. So this we have seen, this will be along negative z direction. Okay, along negative z direction. So VB, okay, VB. So V is along x direction, we can say Vx, Vy, and this is z direction. So this was the fact. Now we'll see how we can find out the, so the question is the following. Okay, so the questions are, see this first question, so there are two different metallic strips of the same material. Okay, same material, that means charge carrier densities are same, lengths are same, but widths are different. Okay, so in that case, so the points, 2 points K and M are symmetrically located on the opposite faces parallel to xy plane. And V1 and V2 the potential differences. Okay, V1 and V2. So if V1, V2 are the potential differences for two different metallic metal strips, then see which of the following are true. So we have to see when W1 is equal to W2 and D1 is equal to 2D2, then V2 and V1, what is the relation between them? So this can be actually found out very easily. We can find out very easily if we can find out the potential first of all. How potential difference? See, we have seen already E is equal to V and V, right? So how do you find out potential? Potential will be found. See, potential actually develops across z direction, right? Potential develops across z direction. So potential, we know potential is equal to E into W. E into W. So what is E? E we know. So this is Vx and with the Vy, Vx Vy into Y. So this is the potential. And see what is this Vx? V is the velocity of the charge carriers along x direction. Okay, so what is this this W? W is the width. Width. So electric field has been produced between these 2 points. So this is the W. So we can find out potential between these 2 points. Okay, so we have already got this W. So we have got the potential. Now what we need to check is that how D and W effect. See, W is directly coming here, but is there any way to include D and L? L is the length, okay, and D is the thickness, so that it is possible to include here d and length and width, sorry, length and thickness. So the thing is, see, it will be potential will be anyway. Okay, let me write it here. Potential will be developed along the z direction, and that is Vz is equal to velocity along x-axis. We have seen By and into W is the width. Now see, we know the current, see current, we know actually, see from electricity we know current is the current density into area. So how do we get area? So how do you get area? See, area will be obtained length and breadth. If we multiply length and breadth, then we will get the area, right? So it is Ix. Okay, so uh, so from here Jx we can find out Ix by area. Area is actually length into breadth. Length is this, breadth is this. Length into breadth we have found out. And see, what is J? J is actually NeV. V is the drift velocity. So this is NeV. NeV, and that is equal to Ix Lw. Okay. So from here, see, if I put the value of this Vx here into this equation number 1, and here equation number, say, so this is Ne here, so equation number 2. So from equation 1 and 2, what we get from 1 and 2, what we get is that Vz is equal to, so Byw into Ix by N into E into Lw. Now see, Ww goes off. Okay, Ww goes off, and B, this is By obviously, and Ix N into electronic charge, and this is L. Okay, so Byix N El. So this is the Vz. I'll write it down here. Okay, I may have one more page. Yes. So I have got Vz, the potential to be Ix By by Ne and L. Ne is the charge. I can write that as Q also. See, we have got now the potential. The question was when D, see here we have this relation first. Okay, if W1 is equal to W2, so I can write it for both. So this is Vz for 1, that is Ix By, everything is correct, everything is same. Here length is also same, length is also same, L. Okay, width is also same. Okay, and for V, so this is for object 2. ix by e NEL. Now the question was, the first option was W1, W2, then D1 is equal to 2D2, and then it will be V is equal to 2V1. So this we have to show whether it is correct or not. Okay, so W1 is equal to W2, we have seen already. Okay, so length is the same. Length is same. It is see, it is actually this is first option. Second option, let me write the option itself. W1 is equal to W2, D1, D2, 2D2, then V2 is equal to V1. Option C says if W1 is equal to 2W2, D1 is equal to D2, then V2 is equal to 2V1. And option D says if W1 is equal to 2, W2, D1 is equal to D2, then V2 is equal to V1. So these are the options we have. We need to actually find out what is true. Okay. So both of them are having the same length for this question actually. Have the same length, but widths are different and thickness are different. See, if we see this n is actually the total number of charge carriers divided by volume. Volume is L, W, and D. If we put this here in this equation, see one expression I'll write. So this is N, L goes, W divided by, sorry, into D here again, E into L, L goes off from both sides. So you can see this, see same material, for same material, the number, this number may be the same, okay, since the length is also same, but if the widths are different, then this number will vary. See, this is the number density, this will vary, this is same, but the total number of charge carriers will vary if this and this are different. That you can see here. Both are directly see then Vz is directly proportional to W and Z. Now look here, if W1 is equal to W2, D1 is equal to 2D2, D1 is equal to 2D2, then V2 is equal to 2V1. That is for sure. That is for sure because it is directly proportional. Even with width also, if it is width, then see how it happens. If the widths are with 2, okay, so V2 okay, so we'll check once again. So we have got one option correct. This option is correct. So option A is correct. So if W1 is equal to W2 and D1 is equal to 2D2, then V2 will be equal to, oh no, V2 will be equal to 2V1. If D1 is equal to 2D2, okay, there is some issue. We'll see that once again. So what was the question? We'll just see here. Consider two different metallic strips, 1 and 2, of the same material. Okay, so okay, so we were all the way correct. Fine. So we had seen, okay, let me just write one point here. See, we have got potential difference B as V, Y, Vx, and W. That is fine. Now we know the total current will be actually N E A Vx. Okay, so that we know. So this is actually current, this is density current. Okay, so there was one more term which we have already left out. So that is actually this area will be, actually area is not length into breadth. Actually we need to take D into W. That was the point. Okay, all right, so there was the simple mistake. So we need to take care of this A to be equal to, A will be here, A will be there, and A can be written as Vx W into D. Okay, so this is the current. Okay, so if that is the current, then see we need this Vx and W multiplication of this. So this we can find out I divided by, so this Ne here and D, Ne into D. This I can write. So you look, Vz will be Vy I, this is also along I x-axis, and Ned. So voltage is actually inversely proportional. So voltage is potential is inversely proportional to D, and this is directly proportional to W. So this point we have to take care. Now we'll go to the question. See, we have got that Vz is directly proportional to W, and Vz is inversely proportional to D. Inversely proportional to D. Okay, now see, when we say this W1 is equal to W2, then potential V1 and V2 is equal. When D1 is D2 equal to D2, that 2D2, when D1 is 2D2, that means your V1 by V2, what it will be? So Vz by D1 divided by Vz by D2, Vz by D2, all other like all other are equal. Vz even Vz also equal. So D2 by D1. Okay, D2 by D1. And what is D1? D1 is 2D2, so it will be half. Therefore, this will be V2 will be 2V1. V2 will be 2V1. So this option is correct. Okay. Now one more point is, see, look, this I'm directly saying this is another point which will be correct, because Okay, so look here, another option. So when W is equal to 2W, sorry, 2W1 is equal to 2W2, and D1 is equal to D2. Okay, so then V2 will be equal to V1. Okay, all right. So this option also will be correct. That you have to check once. Okay, how it is. All right, we'll go to the next option, like next problem related to this itself. See, to solve this problem, what we need to do is, see, consider two different metallic strips. That means there will be different number density, N1 and N2, number density of charge carrier. Length, width, and thickness are all same. Okay, so you need to actually find out the expression for the potential developed in terms of N. So we have seen that was found to be this NED. So it is actually inversely proportional to the charge carrier. Okay, Vz is inversely proportional to the charge carrier. And how it is related to magnetic field, you have to see. Okay, how it is related to magnetic field. We have seen already. We have seen that Vz is directly proportional to Vy. So there are two proportionality relationship we have already obtained. So now we can actually find out. See the option 1, B1 is equal to B2 because directly proportional. Fine. N1 is equal to 2N2. See, Vz is inversely proportional to, so Vz for 1, Vz for 2. Okay, so that was V1 by V2, say. Okay, V1 by V2. So inversely proportional means it will be N2 by N1, and it is given N1 is equal to 2N2. 2N2 means it is half. So we can see V2 is equal to 2V1. So this is correct. Option A is correct. Now we have another option. See, when B1 is equal to B2 and N1 is equal to 2N2, then it is not correct. Okay, now we'll see with magnetic field. See, when B1 is equal to 2B2, that means, okay, let me do it here. So V1 by V2 we are writing. So it is actually, see, B1 by B2. I am just writing other parameters the same, so I'm not keeping them. B2 like this. So if B1 is equal to 2B2, then it is 2B2 by B2. So you look here, V1 will be equal to 2V2, or V2 will be equal to 0.5 V1. Okay, that means this option C is correct. This is not correct. Okay, so this is how you have to find out the answer. I think there was a simple mistake we had done. We'll just cross check this point once again. So this was correct. Another option was this correct. So we had seen, we'll just cross check once again. This is a long question. Actually, there are two questions related to the same paragraph. So we had to actually understand all the points. For a given current flowing through them in a given magnetic field, the correct statement. Okay, correct statement. So we had to find out relationship. See, Vz was Ixby by Ned. So this is the relation, right? So look, this when we have same W, we don't bother other things. So we have, see, V1 by V2 is, see, this is inversely proportional, so D1 will be here and D2 will be here. So this was correct. So when D1 is 2D2, then it will be half. So D1 is equal to 2D2 at that condition. And so V2 will be 2V1. Okay, this was the thing. So the first option is correct. What about this option? This option, see, this, if this is true, this is not true, that is for sure. Now we'll see this W1 and W. So these are, what are the cases? So in this case, look, if W1 is 2W2, so in that situation, what is correct? Okay, first of all, this Vz actually is devoid of, if we go with this, it is actually doesn't depend on the width itself. Okay, it does not depend on the width. Okay, so it does not depend on the width. That is what it means. So the potential develop across Z axis does not depend on width. Okay, does not depend on the width. That's how whenever when D1 and D2 are equal, then V1 and V2 they are equal. Okay, so this option D will be correct here. Okay, this option will not be correct. Okay, so option D is correct. Okay, because it does not depend on the width itself directly. So that was the question. Actually, we have another question. We'll quickly solve that. Okay, so this is also paragraph based question. It will not take more than 5 minutes. Okay, so we'll go for it. We'll see, I think there are some parameters missing. We'll just see the question. A point Q is moving it is a point charge Q is moving in a circular orbit. So say this is circular orbit of radius r. A point charge Q is moving. Okay, so Q is moving. This is in the xy plane, so it is in the xy plane, y, and this is xy plane with angular velocity. This sign is omega, angular velocity omega. This can be considered, this is considered actually, this can be considered as equivalent to a loop carrying a steady current Q. I'm sorry, this is not QW by 2 pi. Okay, I'll tell you what. So when a charge carrier, say some positive charge or negative charge, when they are undergoing a circular motion, we can take that, or we can consider that as a current loop. Okay, that is a current loop. where a constant current I, how you find out I, current Q by time period of revolution. So Q is this and time period of revolution is 2 pi by omega. So omega, Q omega by 2 pi is the constant current that is flowing. So here this current is not Q, that is Q omega by 2 pi. A constant current Q omega by 2 pi is flowing in the loop. A uniform magnetic field B along the positive X is now switched on, which increases at a constant rate 0 to B in 1 second. That means if we require dB by dt, we can write, so this is dB means B, 0 to B, and dt means 1 second. So dB by dt is 1, sorry, dB by dt is B only. That we can write. So what we have found out, current is to be QW by 2 pi, this is given, and change in the magnetic field 0 to B, that happens in t is equal to 1 second, that is given. Assume that the radius of the orbit remains constant, that means r is constant always. The application of the magnetic field induces an EMF in the orbit. The induced EMF is defined as the work done by an induced electric field in moving a unit positive charge along the closed loop. Okay, that means, see, when an electric field is changing, during that time when you are actually moving the charge along the circular orbit, so in that case you have to actually apply certain force against the EMF developed. Okay, so you have to do certain work done, and that work done will be converted to electric energy or electric EMF. Okay, induced EMF is actually coming from there. It is known that for an orbiting charge, the magnetic dipole moment is proportional to the angular momentum with a proportionality constant. This is gamma, a proportionality constant gamma. Now I have two questions. So one is this: the magnitude of the electric field induced in the orbit. That is the first question. At any instant of time t during the time interval of magnetic field changes. Okay, change. So electric field we have to find out. See, electric field is actually, so this is, see, this is omega, velocity is omega, and this is q omega by 2 pi, and this is gamma. So electric field we know E into dl is actually EMF. Okay, EMF. So how do you find out EMF? EMF magnitude we have to find out, right? So EMF is actually d phi by dt, that we know all. So d phi by dt, that means phi is b into a, area, ddt, and see this phi, so magnetic field is changing from 0 to b, so then d phi by dt is actually b by t, and area is pi r square for the loop. Okay, so b pi r square, capital R square by t is 1 second. Now if we put it this equation, so we'll go to the next. Okay, so here itself, let me, so put into this equation, this is electric field, actually dot product, it should be dot product. So E dot dl is equal to EMF into dl. So what is dl? Dl is the circumference. So E into 2 pi r is equal to the EMF induced. So what we have found out, that is b pi r square, b into pi into r square. Now look, pi goes off, 1 r will be going off, so electric field will be actually br by 2. So br by 2, so b will be, so this is the magnitude of the electric field. The br by 2, that is the option. Now we have to solve another problem, that is So these are actually two. The change in the magnetic dipole moment, magnetic with the orbit at the end of the interval of time of the magnetic field changes. So a magnetic dipole moment. So how do you find out magnetic dipole moment? Magnetic dipole moment can be found out I into A. Magnetic moment, sorry. See, magnetic moment again, it is directly proportional to, see what is given. See, the magnetic dipole moment is proportional to angular momentum proportionality with the proportionality constant gamma. So this we can actually found out. This is the relation we can use. So with the proportionality constant mu is equal to gamma L. So this equation we can use. This is given. Now what is, how do you find out L? See, we know dl by dt is equal to torque. So how do we write a torque? How do we write torque? See, there is electric field, we know, electric field into the charge. This will be the force into radius. So this will give you the torque, force into perpendicular distance on the charge particle. See, if this is the charge particle, there will be force, and this is the distance. So this is the force and this is the distance. Okay, so this is how. Now if this is the torque, the electric field we have already obtained as Br by 2, and Q is also constant term, and see this is R. So we have B Q R square by 2. And now if you want to find out what is L, we have to integrate 0 to L, and here this all the terms are actually constant, so we'll not bother about that, and dt integration will be 0 to t. Okay, 0 to t. So we'll get actually B L is equal to BQ R square by 2. Okay, BQ R square by 2. All right. So we get BQ R square by 2. Now we know this change delta L is mu is directly proportional to L. Okay, that is what we can use now, make use of that. So we'll make use of that. So gamma into L is BQ by 2 into R square. So this is what it is. And obviously we know this mu is actually always in the opposite direction to L. Okay, mu will be along this direction and L will be in the opposite direction. So they will be in the opposite direction, so there will be obviously a minus sign, okay, over here. So then we get mu is equal to gamma BQ R square by 2. I hope there will be option. So this is the option. So option B will be the correct answer. So why we have taken minus? Because we have seen that the magnetic moment and the angular momentum, they will be always opposite to each other. Okay, because it is we can go for that. So R cross P. Okay, R cross P. This is in the xy plane. P will be V is again this. So R cross P will give you eventually negative this, and IA, if it is okay. So this is actually not mentioned what is the charge. It is positive charge. So anti-clockwise, clockwise, it doesn't mention. But anyway, we know this. The magnetic field and magnetic moment and angular momentum, they will be opposite to each other. So that's how there will be a minus sign coming. Okay, so option B will be the correct answer for this question. Okay, so we'll stop it here for today. Thank you for your patience. Bye.